Hello again. So in this section, what we're going to do is to talk about the equations that describe the motion of particles moving with constant acceleration. And this is a very important topic in physics because it simplifies our life. Like before we get to like non-constant acceleration, we need to know how the particles move under the constant acceleration. Now, these are called equations of motion, and they can be used to describe a wide range of everyday phenomena. For example, in an idealized world, and we are talking about an idealized world, not the real world, with no air resistance, falling bodies have constant acceleration. And if you think about it for a moment, it becomes really um, interesting. So, if there is no air resistance, a feather and a stone, they both fall with the constant acceleration, meaning they fall at the same time if you just like let them fall without giving them the initial velocity. And that is the acceleration that we call the gravitational force of the earth. So with the gravity of the earth is what pulls all the objects down, right? So if there is no air resistance, any two objects or any objects, they would just fall with the same acceleration with g, the gravity of the earth. And actually this is the experiment that has been done in, I think it says in Florida, if I remember correctly. And they make a chamber, a vacuum chamber, which means that there is no air resistance in that chamber. And then they let a rock and a feather just fall, without any air resistance. And they observe that actually they both fall at the same time. All right, moving on, let's talk about the first equation of motion, what we call velocity as a function of time. As I mentioned in the previous section, if a particle has a constant acceleration, which means the same acceleration at every instant of time, then its instantaneous acceleration, a, is equal to its average acceleration, which we called a sub av, average acceleration. Now, the definition of average acceleration was that average acceleration equals to final velocity minus initial velocity divided by final time minus initial time. All right, now, if a particle has a constant acceleration, then this average is just equal to the instantaneous acceleration. Now, it is arbitrary to choose the initial and final times. For example, if we let the initial time to be 0, so if I just let the t initial equals to 0, and then I call the initial velocity to be v naught, which means just like the velocity at time 0, then we can just write a equals to v. So I'm just neglecting the f here, the sub f here, because it's just like v at every moment, minus v naught equals to t minus 0. So I chose my time 0 to be 0, or my initial time to be 0. Okay, then I can write v minus v naught equals to a t, or v equals to v naught plus a t. So this is my first equation of motion, which is the velocity as a function of time. Okay, so this is equation 2, 7 on your book. let's just do an example here. So this is exercise 210 on your book. So please read the problem with me from your book. It says a ball is thrown straight upward with an initial velocity of positive 7.3 meters per second. So again, I'm writing the known. Okay, when it says the initial velocity, it means that V naught or VI. But since I change it here, so let's call it V naught. So it is positive 7.3 meters per second. If the acceleration of the ball is downward with the value of negative 9.81 meters per second squared, so A is negative 9.8 meters per second squared, find the velocity of the ball after t equals to 0.45 second. So the unknown here is what is the velocity. Here I'm sketching this problem. So at the beginning I have the initial velocity of 7.3 and then it goes up and it says the acceleration is constant and it is down, so it's negative 9.8 meters per second squared, which is the gravity of the earth, by the way. And then so find the velocity of the ball after, so here after some time, which is 0.45 seconds, we want to find the acceleration, the velocity. Okay, now I need a proper equation. So the proper equation is equation 2.7 on your book, which says V equals to V naught plus AT. Okay, so I'm supposed to find V and I have everything else. So I just go ahead and replace the numbers. So V equals to 7.3 meters per second plus I have a negative 9.81 meters per second squared times the t, which is 0.45 second. See how nicely this square root cancels with this s. So I have both meters per second in this term and another meters per second in this term, which is showing me, like if I do the dimension analysis, it shows me the consistency between the units. So if you find this, then V will be 2.9 meters per second. So always put the unit and always box your final answer. That was all about the velocity as a function of time. Next, we are going to study position. So position as a function of time and velocity. So this is the second equation of motion. All right, so this says how far does a particle move in a given time if its acceleration is constant. All right, so now we're looking at the position, not the velocity anymore. Now, for that, I want you to recall the definition of average velocity. Remember that the average velocity was the change in position or the displacement divided by time. So I'm going to break this into x final minus x initial divided by t final minus t initial. Now, using the same identifications that we talked about previously for initial and final times, so I can let x initial to be x naught and then t initial to be 0. So x naught simply means the position at time 0. And then I can write x final just to be x. Okay, so with this new thing, V average is going to be x minus x naught divided by t minus 0. So I can write v average equals to x minus x naught divided by t. And then from here, x minus x naught equals to v average times t. So I can find the position to be x naught plus v average times t. So this is the second equation of motion, which is equation 2.8 on your book. This equation is fine as it is, and in fact it applies whether the acceleration is constant or not. But a more useful expression for the case of constant acceleration, we can obtain it by writing v average in terms of the initial and final velocity. So I can just write, because it's an average after all, right? So I can write v average to be half of the initial velocity plus the final velocity. So this is simply just an average of two values. All right, so if I just use this term instead of the average, then I can write, let me go to the other page, then I can write x to be x naught plus half v naught plus v times t. And this is another equation. This is equation 210 on your book. Now, the equation, like the equation 27, is valid only for constant acceleration, okay? But the equation, like equation 2.8, is valid in every case. Now, the equation 210 is valid only for the constant acceleration. If I want to just draw a graph for this case, so if I just draw the graph of v versus time for the constant acceleration, and we know that, okay, let's start with the initial velocity. And when I say constant acceleration, it means that the slope of v versus time should be constant, okay? So this gives me time t. And remember that my starting point is at time 0. Okay, then the final, we called it to be v, and then v average is something somewhere here in the middle, right? So it's in the middle of, so this is my v average, which is half v plus v naught. Okay, quickly I'm going to show you what happens if the acceleration is non-constant. So this is for constant acceleration. Now, if the acceleration is not constant here, so this is non-constant acceleration, what happens here is that the velocity curve is nonlinear. Now, it would be, so let's start again at v naught, which is at time 0, but then instead of having a linear graph, I'm going to have something like this. And this is the end point here, okay? Now, and this is the end velocity or the final velocity. Now, I cannot say that the average velocity is the midway between the initial and final velocities anymore. So the average velocity is no longer midway between the initial and final velocities, but it would be somewhere maybe around here. An example that I'm going to do for this case is called full speed ahead. Now, this is example 211 on your textbook, page 35. It says a boat moves slowly inside a marina so as not to leave a wake with a constant speed of 1.5 meters per second. So constant speed, this means that the initial speed and the final speed is going to be the same, and that is 1.5 meters per second. Okay, so this is the known. As soon as it passes the breakwater, leaving the marina, it throttles up and accelerates at 2.4 meters per second. All right, so acceleration is going to be 2.4 meters per second squared. All right, so the unknown is A. How fast is the boat moving after the acceleration for 5 seconds? Okay, so if it moves for 5 seconds, so I'm gonna erase this because this means that the final velocity is not constant anymore, but it has accelerated. So we are going to find this acceleration here in part A. And then it says in part B, it says how far has the boat traveled in these 5 seconds? So I'm gonna find x2. Okay, step 2 is to draw a sketch. So in my sketch, I'm choosing the origin to be at the breakwater. Okay, so let me just sketch here. This is a very nice breakwater. And then I choose my origin to be here. So this is my 0. And then the positive x direction is going to be the direction of motion. So this is my x axis and this is the water. Okay, and then I have the boat. How am I going to draw a boat? Okay, this is my boat. And then it accelerates at some point with 2.4 meters per second squared. And this is me and the boat. Okay. So because I chose my origin to be at the breakwater, after which it accelerates, I can write here that the initial position is at 0. Okay, and then the initial speed is at 1.5 meters per second because before this time it was moving with a constant speed. So I do not care about before the, the breakwater when it started to accelerate. All right, now I'm going to need a proper equation. So because I need to find in part A the velocity, and I already know the velocity naught, so V naught, I know A and I know T, so the proper equation that gives me the value for velocity is going to be V equals to V naught plus AT. Okay, so this is equation 2.7. So in this part, I'm going to use this. And then I'm going to write it here because I have more space here. So velocity is going to be 1.5 meters per second plus 2.4 meters per second squared times 5 seconds. So this is going to be 1.5 meters per second plus 12 meters per second, and the final result is 13.5 meters per second. So it has the unit, and I'm going to box my final answer. For part B, where it asks for the position, we have the knowledge of the initial and final velocities, and we can relate the position to time using equation 210. So the equation that I'm going to choose here is this equation, x equals to x naught plus half v naught plus v times t. Alrighty. Now, I'm going to find x by replacing the values. So x naught, which is the initial position, is 0 because I chose it to be at the 0, plus half. My initial velocity is 1.5 meters per second, and I can again use this because my acceleration is constant, plus the velocity at the end is 13.5 meters per second times 5 seconds. So okay, this 0 is useless here, so it's going to be half 15 meters per second times 5 seconds. Okay, so the result is 37.5 meters. Box the final answer. Do not forget the unit, and I hope that everyone already know this, but I'm gonna emphasize again that when you have like a big equation like what we have here, first you're going to add the terms together and then do the multiplication, because if you don't do and you just multiply 1.5 by 1/2, then it will give you the wrong answer. So you need to do the parentheses first, or inside the parentheses first, and then do the products. Okay, so we learned how to find position as a function of time and velocity. Now we want to find a position as a function of time and acceleration, and this is the third type of the equation of motion. Okay, so in the previous example, the velocity of the boat is a function of time, right? Now, how this distance traveled by the boat is going to correspond to the velocity versus time curve, which is the acceleration. Okay, at first, I'm going to use this equation, and instead of v, I'm going to replace from the other equation that I had. So I can write v average to be half v naught plus, and then instead of v, I just replace v naught plus a t, right? So this gives me v average to be v naught plus half a t. Okay, let's call this equation I. Next, what I'm going to do is that instead of v average, which is half v naught plus v, that is my equation 1, I'm gonna replace this term in the equation that I had for location. So I have x equals to x naught plus, so instead of half v naught plus v, I'm gonna put equation number 1. So v naught plus half a t times, and then I have another times t here. Okay, so what I'm going to do is that I'm going to just simplify and organize this equation. So I get x equals to x naught plus v naught t plus half a t squared. Now, this is my important equation of this chapter, equation 211, and this gives me the position as a function of time and acceleration. If you want to do something fun, just go ahead and check it for the dimension analysis. But then for us, let's go ahead and solve a problem, which is exercise 212 on your book. It says, repeat part B of example 211 using equation 211. So I am required to use this equation and repeat part B of the boat example and find the position of the boat. Okay, so this is easy because the equation is already given to me. So I'm going to just replace the values that I had. So x equals to, remember that the initial position I considered it to be 0 plus, and then the initial velocity was 1.5 meters per second, time was 5 seconds, plus half, the acceleration was 2.4 meters per second squared, and time was 5 seconds squared. Okay, so I let you use your calculator and find the final value, and you will see that it is equal to 37.5 meters. Okay, so we got the same result. Now, not always you have two equations to use. Sometimes you only have, for example, the acceleration and time, and you do not have the velocity, the final velocity. So you have to use this equation here. So depending on what piece of information the problem gives you and what piece of information you have to drag, you need to find a proper equation out of the many equations of motion that we are introducing in this chapter. This is the final equation of motion with constant acceleration, and it relates the velocity to position. Okay, so I'm gonna just add a quick note here that you are not expected to know the derivation of the equations. You just need to know how to use it. Okay, so whatever I do here to derive these equations for you is just solely for your own information. You do not have to memorize it. You just have to know how to apply the equation. So I'm gonna start by solving for the time t in equation 2.7. So equation 2.7 was v equals to v naught plus at. So I'm going to solve this for t, okay? So I can write this to be v minus v naught equals to at, or t equals to v minus v naught divided by a. Okay, now we substitute this result into equation 210. So equation 210 was giving me x equals to x naught plus half v naught plus v times t. So I'm gonna substitute for t here, and I get x equals to x naught plus half v naught plus v times v minus v naught divided by a. Okay, so what I have here is this part. Look at this part. V naught plus v times v minus v naught. Okay, so this is a famous expansion. So I'm going to write it as v plus v naught times v minus v naught. So this is going to be v squared minus v naught squared. So this is a famous expansion in math. And then I can write x to be x naught plus half v squared minus v naught squared divided by a. So let me just go ahead and write it in a more neat way. So I can write x equals to x naught plus v squared minus v naught squared divided by 2a. So this is one instant result. So because I want to find the velocity as a function of the position, I'm going to solve this in terms of v squared. So let me go to the next page. And I can rearrange that equation and write v squared equals to v naught squared plus 2a x minus x naught. All right. So once you find v squared, then it is just a matter of taking a square root to find velocity. So this is equation 212 on your book. All right, example. It's called takeoff distance for an airliner. So that is example 214 on page 38. It says jets at John F. Kennedy International Airport accelerate from rest at one end of a runway and must attain takeoff speed before reaching the other end of the runway. All right. A. Plane A has acceleration A and takeoff speed of V sub TO. This is one of those problems that instead of giving you numbers, it wants you to work with symbols. And actually, I like them better than the numerical problems because it's just like easier to work with them. So the known of the problem is that acceleration is A. The final velocity is called VTO because it says that it attained the takeoff speed before reaching the other end of the runway. Okay, so when it says the takeoff speed is VTO, it means like at the end of the runway. Okay, so what it wants us to find, which is known, unknown, it says what is the minimum length of the runway delta x a. Okay, so let me sketch. So again, I'm going to use the positive x-axis to the right. So the plane okay, so this is the plane, starts with 0 initial velocity, right? Because it starts from the stop, and then accelerates in this direction, and finally it reaches the point that it has to take off. So here the plane has to take off, right? So at this point, let's call this x, and this is my x initial, which I considered it to be 0 because I want everything to start at time 0. Okay, so what it asks me is this length, which is delta x a because it's for plane A. All right, so what equation do I need? Look, I only have the acceleration, the velocity, the initial velocity, and I want the position. Okay, so it's just like very logical that I use equation 212. So I'm going to write v squared equals to v naught squared plus 2a x minus x naught, right? Okay, so v squared is going to be 0 squared plus 2a, and sorry, so here the v is called VTO, and then x minus x naught, it is the length, so it is delta x a. So I'm supposed to find delta x a. Okay, so from here I have delta x a equals to v TO squared divided by 2a. So this is just in symbols. All right, so if you had a numerical value for the velocity at this point, right, and then you had the numerical value for the acceleration, you could just easily find the minimum path or the length of the path of the runway. So what I highly suggest that you do right away, meaning pause this video, go to your book and look at section 2.6, applications of the equations of motion. and there is a table on your book, table to find, that gives you exactly the variables related to the equation, what equation you need to use, and the number of the equation on your book. So you have 1, 2, 3, 4, 5 equations. Each of them have a certain variables related to it. And then the book solves plenty of examples for you for each case. So this is something that you should study on your own, and that is your reading assignment here. Reading assignment is section 2.6. Okay, without any doubt, the most famous example of motion with constant acceleration is free fall. And this is something that we talked about at the beginning of this section. So this is the motion of an object falling freely under the influence of gravity. So freely under the influence of gravity. It was Galileo who first showed with his own experiments that falling bodies move with constant acceleration. Now remember that my dog's name is Mr. Galileo Galilei, right? So I named him after this scientist. His conclusions were based on experiments done by rolling balls downward inclines of various steepness. Okay, so what we are going to um, do in this section is to characterize the free fall. Okay, so the word free in free fall means free from any effects other than gravity. For example, in free fall, we assume that an object's motion is not influenced by any form of friction or air resistance. So free from any effects other than gravity, and this is important here. So the only force we need to have is the gravity. So free from air resistance or friction. So the free fall is the motion of an object subject only to the influence of gravity. Okay, next we need to know that an object is in free fall as soon as it is released, whether it is dropped from rest, thrown downward, or thrown upward. So an object is in free fall as soon as it is released. So this is whether it is dropped from rest, thrown downward, or thrown upward. All of these are considered to be the free fall. And then finally, this is the most important thing, is that the acceleration produced by gravity on the Earth's surface, so what we call the gravitational strength, is denoted with symbol G. Okay, so this is the acceleration of the gravitational strength of the Earth. Now, we can call it acceleration due to gravity. So this is acceleration due to gravity. Okay, so in all the calculations that follow in this book and in this course, we use G equals to 9.81 meters per second squared. Now, a quick note, see that the unit is still meters per second squared because this is another acceleration. So it is a type of acceleration. So G is just like A, but this is due to gravity. That is why we call it G. And the final note is that all the equations of motions that we studied so far are correct. Just instead of A, we are going to use G. Okay. Now, example 218 on on page 44 is called lemon drop. So it's, excuse me, it says a lemon drops from a tree and falls to the ground 3.15 meters below. Okay, so what I'm going to do is first I'm going to sketch this so that you see how it is like being done. So this is the tree, lemon tree. So I have a lemon that is dropped, okay? So it is moving downward. All right, so this is the negative y direction. Let's call it just, well, let's call it x because we have not yet studied the two-dimensional axis. So let's call it negative x direction. All right, so I changed my mind again. Let's just call it x-axis. Okay, so my initial position is on top of the tree, so this is my x naught, and I'm gonna label it to be 0. And then the final location of the drop, which is the ground, right? This is my ground, so this is the x, and then I'm gonna call it h because it is the height of the tree. All right, so it asks me how much time does it take for the lemon to reach the ground and what is the lemon's speed just before it hits the ground. Okay, let's go ahead and write the known of the problem. Okay, so x naught is going to be 0. So how I chose it. The acceleration is going to be equal to g because it is just falling due to the gravity and I'm moving with the direction of the gravity. So it's going to be positive g. And then the height of the tree, which is my x, it says 3.15 meters below. Okay, so the initial velocity is 0 because it is just dropped. And what I need to find, which is the unknown, is t. And then what is the velocity of the lemon as it hits the ground. Okay, so for t, I let you just think for a moment and see with knowing x naught, a, x, v naught, and wanting to find t, what is the proper equation to use. All right, so I let you know what. So part A, I'm going to use this equation, x equals to x naught plus v naught t plus half a t squared. All right, so let me just go ahead because I have bunches of zeros. Let me just go ahead and write them down so we know that we can get rid of the zeros. So x naught is 0, v naught is 0, and then half, and look at here, a equals to g, so this is g t squared, right? So I have simply x equals to half g t squared. I can solve this for t. T becomes square root of 2 x divided by g. Okay, I'm going to replace the numbers here. 3.15 meters divided by 9.18. My bad, not 9.18, 9.81 meters per second square. So if you solve this, the result is 0.801 seconds. Unit and box, do not forget that. For part B, when it asks about the landing speed, or V, so in this part I'm going to find the landing speed. So the equation that is proper to use here, and just like the simplest one, is going to be V equals to V naught plus GT, right? So originally it was V equals to V naught plus AT, but I know that A equals to G here. So let's replace V naught is 0 plus 9.81 meters per second squared time the time that I got from the previous part. So velocity is going to be 7.86 meters per second. Okay, so I could either use this equation, or, so this is just an or, you do not have to do it. It's just like for me to show you an alternative. So I could use even this equation, v squared equals to v naught squared plus 2a delta x. I could write this to be v naught squared. Oops, v naught is 0, so why should I put it even here? So 0 plus 2g delta x, which we called it h, okay? So that would give me v equals to square root of 2gh, or square root of 2.9.81 meters per second squared times 3.15 meter equals to 7.86 meter per second. So this is the same. So both equations will give you the same number. So this free fall from rest, just like what you saw in this example, happens so often and in so many different contexts. Now, that is why it deserves a special attention. So if something is falling freely from the rest, then I can just use this equation x equals to x naught plus v naught t plus half a t squared. And because it is my liberty to choose the zero position or the initial position, I can always put my 0 where the motion begins, and then because it is falling from rest, so my initial velocity is 0, and then because it is a free fall, so it's due to gravity, my a is g, and then t squared. So I can just write x equals to half g t squared. So similarly, v, that is v naught plus at, so this is going to be 0, and a equals to z, so v becomes gt, right? And then similarly, v squared equals to v naught squared plus 2a delta x, so v squared equals to 0 plus 2g x minus x naught, so this x naught is 0, so I can just write v equals to square root of 2gx. So these equations always is correct for the free fall from rest.